Hello, everyone. Welcome to class 2 of the machine learning course. Just to again familiarize you with the SIGGRAPH policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means please exercise consideration and respect in your speech and actions. Refrain from demeaning or discriminatory or harassing behavior and speech. And please be mindful of your fellow participants and be excellent to each other. All right, so let's begin. Last time we covered how to look at different data, and we'll have a guest today. Whenever she's ready, she'll come in and we'll cut her in to the chat. And while she's getting ready to come on to the show, we will continue on with our education today. So we'll do a quick recap. We talked about the introduction and the housing data that we looked at last time, and we'll build our first neural network for regression for predicting house prices based on the data that we have. Visualize the results, and we'll build a second neural network for classification. And just to recap briefly, that given some data, how do we approximate a function that represents the data? So that's the whole idea behind building the neural networks. Like, we want to approximate a function that represents the data, and we do that by minimizing the prediction error. And as you saw in case of minimizing the squared errors, that we try to fit a line in linear regression through all the data points as closely as possible. And when you minimize that error, or the sum of all the errors, you are essentially doing gradient descent and try to find a minima that is global for all those errors. So to recap some terminology that we covered last time, that you are normally given a set of attributes or features, as they're called, and then a set of known outputs based on those features, and that becomes your ground truth. So that's what you're going to use to train your network. So you build a model to train your network, and then you figure out some kind of a loss function. In case of least squares method, the cost function or the loss function was essentially the sum of squares of the errors. And we introduced an activation function that introduces non-linearity into the mix, and that took a form of a sigmoid function or a rectified linear unit. And then we will train the data, and also known as fitting, and optimize for minimizing that loss function. And then we'll evaluate the performance of our network, see if it is behaving properly, it is giving us the correct results as we expect. And once we are satisfied with the network and the results and the training, we are going to start predicting from new data that the network has not seen before. And that part is called inferencing. So we'll use these terms again and again, and you'll get familiar with them, and they form like the core part of like building machine learning models and training them and predicting from that. So it'll be a lot of hands-on today. We'll be looking at two files in particular: housing regression, that we'll build a regression neural network with, and flower classification.
Hi, Rajesh. Nice to meet you. Sorry, I was waiting in the
all right.
room.
No problem. So, all right. So we have our guest here, Bindu. Very warm welcome to you.
Thank you. Nice to meet all of you.
So happy you could make it. And let me go back to your.
I was waiting in the waiting room, but here we are. Okay, nice to meet you.
There it is.
Yeah.
No problem. I think this is, you're busy, and this is totally fine. And we'll just do it very casual and easy going. So again, very warm welcome. And for the audience member who don't know you, could you describe a little bit about yourself, your journey into this world of machine learning?
Totally. Thank you. And thank you for having me on. My name is Bindu Reddy. Hi. Very nice to meet all of you all. I'm the CEO, co-founder of a company called Abacus AI. Abacus, we like to think, is the next generation platform for creating, building, deploying, and training models, machine learning models at scale. Before Abacus, before I started Abacus, I was at Amazon Web Services. So I was part of the AWS AI and was responsible for an organization called AI Verticals, where we were building out various different AWS services with specific applied AI uses and in various different domains where AI could be used in a real world sort of way. And so the examples of these would include things like real time deep learning based personalization, deep learning based forecasting, so basically time series forecasting based on past data, anomaly detection, as well as things like fraud and predictive modeling and so on. And previous to that, I was at a another deep learning company that I co-founded called Post Intelligence. It focused on NLP and NLU, and the idea there was to see how we can use language models to help social media influencers become more more proficient in increasing their followers. So how do you help increase engagement on social media? And finally, before that at Google, I was head of product for G Suite, but also was for a couple of years worked on Google AdWords, where I actually had my first, I would say, encounter with machine learning. So machine learning as it is today is very, very obviously commonplace, and pretty much every company has one or two ML models. I would say a decade or two ago, there were like very few companies which were doing ML. Google, of course, was one of them, and the idea and the kinds of models that were being built were very different. And if you looked at some of the most fantastic things that Google has built, there's Google Search, but there's also Google Ads. And the idea was to learn patterns from what advertisers and consumers did with those advertisements in the past, and then try to predict the future, right? That's how I kind of got hooked a little bit into ML. It was too much of a black box then, and over time it's become less of a black box. And really, my journey was really informed around the real-time or the real-world application of ML. So people don't understand how much of a difference machine learning can make to your business or to any kind of business process. A classic example of this is without machine learning today, there would be no Facebook, there'd be no Twitter, there would be no Google search. Of course, there'd be no Alexa and so on. But the obvious things like Facebook, Twitter, Google search, people don't realize how completely broken it would be. And when I came face to face with that, I was fascinated by it. And so over time, I've kind of become more and more, familiar, as well as become more and more involved in that space.
Oh, that's great to hear. I think that's a fantastic journey. And can you describe what your company does and what kind of solution it's providing to what kind of clients?
Yeah, of course. So what Abacus does is it's meant for companies who want to embed machine learning or deep learning into their apps or business processes, what have you. And so we kind of focus, as of now at least, on a plethora of structured data solutions, or basically machine learning models which involve structured data. So this is basically data in databases or data warehouses or what have you. And it's an end-to-end solution. So it's basically, think of it as a service which helps you kind of ingest data from any structured data source. So it could be Snowflake, Redshift, what have you. It'll help you not just ingest data, but it'll help you set up those data pipelines so you can get the data on an ongoing basis. You can then wrangle and transform the data to your heart's content. So you can basically join tables, create new features, do featureization, set up a real-time feature store. So all of that stuff which you need to do with data becomes super easy. You're not writing any Spark scripts. I mean, I think the bane of a data scientist is Spark. So we kind of help you make data transformations. We help that part become much, much easier. And then afterwards, you can either choose to create your own model using a Python notebook, like your Jupyter notebook, or you could use our AutoML service, which creates a deep learning model based on your use case and your data. So we actually do something called neural architecture search to find the right neural net which fits your use case and data. And then once your your model is trained, you can evaluate various different models, your own models, models created by the system, choose the model which works best for you, and then put that in production. So then it's now running in production, you have it deployed, and the system is completely automated. The whole monitoring of the model, predicting on a regular basis, writing predictions back, the whole end-to-end system is encompassed in one service. We think this is the future of AI tools, at least, having a service which is a platform of sorts which helps you do all of this. And Abacus is playing in that space.
No, that's great to know. I think that just the burden of processing the data, training it, and deploying it, I think that can be bigger than coming up with more. And I think we are used to seeing all the news reports of like image-based models and things that are more visually appealing. But I suspect that many of the models that are deployed in currently are operating on data and doing regression of basic kind, but not complicated models. Is that correct?
So I would say, I won't say it's the word complex is actually maybe a little bit of a misnomer. I agree with you. A lot of the models are not vision models, primarily because not many people have images, right? I mean, a few companies have images. Maybe the U.S. government has a lot of images, but not your standard enterprise. So you do have models which are based on structured data. Now, and yes, they are like far fewer layers. I mean, they're not like these big GPT-3 style large models, but all of the complexity really comes in terms of the data wrangling, the data transformation. And now the problem is, as COVID has happened, it's not really a problem, maybe it's a good problem to have, but the issue is, as COVID has happened, there is this deluge of data. So it's become a big data problem, right? So I would say this is big data machine learning more than anything in some ways, and each data set is very different from the others. So there is complexity in the data transformation, the data cleaning, and sometimes even in how you would model it, because you don't want you want to make sure that of course you're not leaking anything, but also getting all the signal that you can get. But for sure, yes, it's much more prevalent to have the kinds of things I think you were planning to teach in this course as well, right? The regression and the house price. Those are some of the classic models there.
And then you touched on this a little bit. I think a lot of the research that comes out, I think people think that they need to know so much deep math to kind of be in this field, but there must be then a variety of jobs that are about being a data scientist, about being a machine learning engineer, and machine learning researcher. So could you describe some of the roles that you have in your organization?
Yeah, for sure. So on one extreme, you have this machine learning researcher role, which is, as you mentioned, somebody who wants to like write papers to like the top conferences like NeurIPS and whatnot. And there, I think you do really have to have an understanding on how to read these papers that are existent, how to create how to set up new experiments, how to write papers, and so on. And that's that's on one extreme. And then I would say there is this other extreme, which I'm going to call a data scientist role, which is like real world application of like some of these ML models. And these models can be simple or can be a little bit more complex based on what the use cases in the data set is. And there, what you're really doing is it's a role, actually, the data scientist role, I think, requires a lot of smarts, to be honest, because you're having to think on your feet and think about the problem that you have and cast the problem correctly. The skill set there is taking a business problem and like casting it as a machine learning problem. Understanding the ML fundamentals, you don't have to be like a whiz kid, but you have to understand like basics about probability and statistics and that sort of stuff. And then, using the tools that are available to make a reasonable ML model that is in turn actionable in the business, right? So first you take the business problem, cast it as a machine learning model, then you get the machine learning predictions, and then use it back in a business context. And that requires a lot of like creativity. As well as understanding of fundamentals, but not the kind of like, oh, I need to go get a PhD in deep learning. So, so across the spectrum, there are obviously some shades here. There's the data scientist and the ML researcher. There is a ML engineering role where you're basically building, products around some of the infrastructure which is needed. Sometimes you're building techniques to make these models work, but you can see that there is a broad spectrum.
That's great to know, actually. So I think our audience would love to learn a little bit more about like what should they focus on to get into the field. And I know we are covering basic material in this course, but I think that should give them enough of a start. But do you have any other advice for them? Be like what kind of things to read or?
Yeah, I mean, my 2 cents. I mean, it's a good thing that you're having this course. So obviously, that's a great course. It's a great course to attend because I saw some of the curriculum. It sounded perfect. But first thing, if you're a programmer, great. If you're not, I mean, I would strongly urge people to learn and understand Python. I mean, this is probably said 1,000 times on Twitter every day, but Python's like pretty much the language of machine learning. So learn and understand Python. Beyond that, of course, learn SQL and Spark a little bit. Spark tends to be hard, so anything you can do to avoid it, great. But definitely SQL and pandas, which is one of Python's library. And go to courses like this one. There's also a good course that I believe Google has for free, which is only about 15 or 20 hours to take. And then once you have those fundamentals of data science figured out, statistics and probability figured out, and you know how to program, you're ready to build your first model in the real world. And then always remember that toy models are very different from real world models. So when you're working on a course like this and you have an example data set, that will look easy and look simple, and that's good because that's what you have to start with. But once you start working in the real world, there's always complexity. So, being creative about that is the key.
That's awesome. Again, I want to thank you for being with us and sharing your insights. And I personally enjoyed the tweets that you make about the industry, about machine learning in general. I learned a lot from them. Thank you again for being with us. This has been awesome.
Great, thank you, and thanks for having me. And and have fun learning.
All right, bye-bye. Thank you.
Bye.
All right, so that was Bindu. And then if you want to follow her on Twitter, you can find her. And again, she writes some really cool stuff about machine learning and industry in general. So we will go back to our class material. Okay, so that's where we were. So we have shared 2 files with you, housing regression and flower classification. So these are Colab notebooks that you should be able to make copies of. Again, make a copy in your own drive, and then you can start modifying it. So let's take a look at housing regression. We'll do a lot of hands-on coding today. And what I'm going to do is start sharing the notebook live. So once you connect your notebook, you get a free cloud machine, basically, and that is going to help you run TensorFlow and related packages that we have. So essentially, this is a full Python environment with access to a number of packages that we'll be using. So as Bindu said, like Python, NumPy, Pandas, Seaborn, these are all like libraries that we'll use along with TensorFlow. So today will be your first introduction to kind of mixing in TensorFlow with the data analysis and building a model from scratch, basically. So we're going to use the same file we used last time, which is the housing data that we looked at. What I'm going to do is start executing these small little snippets of code. So this part is basically just importing different packages, reading the data, and this data is pretty clean. So again, as Bindu had said earlier, that the data that you use for learning, it's pretty nice and clean, and we're able to learn quickly using that. Real world data is going to be messy, and there'll be missing values. So there are ways in Pandas to remove certain things that are not a value. So you can drop NA. You can use this call to kind of remove things that are non-existent empty spaces in your data, so you can clean those up. Next thing we are going to do is something called normalizing the data. So this is important when different elements of your data have different ranges. For example, the price is in dollars, so it can range from anywhere from 100,000 to 500,000, whereas number of bedrooms is an integer, which will range from 1 to 4. So those ranges are so different that we don't want a large number to influence our training. So what we do is we normalize the data. So normalizing is essentially taking the range of the data and dividing it by, or taking the data and dividing it by the range, and that cleans it up. So because we are using pandas, we can do the entire operation in a single call, because it will take everything and do a vectorized operation on the entire data set. So this is how you do the normalization, which basically this part is taking the range and then is subtracting it from the minimum, and essentially it normalizes the data. And then finally, we're going to just look at the data itself. So if you remember, all these values essentially now are between 0 and 1. That's what normalizing does. And we have about 17,000, or actually exactly 17,000 data points with a number of different attributes. There are 9 of these attributes. The last one is called the median house value, and this is what we would be trying to predict and train for. So once we have that, so in machine learning, what you want to do is not train with the entire data set. What you want to do is keep some aside for testing. Because if you train with all your data, then you don't have data to test with, and you don't want to mix your training and your testing data. You want to test with data that the network has never seen before. So you don't want to bias your network in any way at all. So here, what we are doing by using this fraction option to the sample, we are taking 80% of the data randomly. That's what sample does. So I'll hover on the sample. It takes a random number of samples. We're taking 8 fraction 0.8, which will give you 80% of the data. So we'll take that and assign it to train data variable, and that's our 80% for training, and we'll keep the rest, which is what the drop does. We'll keep the rest for testing. So 80-20 split is what we are using, and you can use different splits, but that's what we will be using is an 80-20 split for training and testing. So next thing we want to do is we want to separate out our Y value. So remember, Y, or the ground truth, that is the result, that column. So that we are going to separate it out. So in the X part, which is the input that we are going to use for training, we keep everything except the house value. So we're going to drop the median house value column from our data and assign it to the X part. And for the Y part is where we want the median house value to be, and that's what our training data to be. So again, we split that into 80% for training, and within that 80%, we separated it out into the X and the Y. So X is the rest of the 8 attributes, and Y is the median house values. And we do the same thing for the testing. So we separate it out into the X and the Y. So let's take a look at what this looks like now. So if you look at that, our 17,000 data points got split into 80%, which is 13,600. And we have that data, and now it's 8 by 8. So because we split the X and we put the Y aside as the ground truth. So same thing for the test data. This is the rest of the 17,000 that got separated from the training. So that's 3,400. And it should also have 8 rows and 8 columns. So that's how you prepare the data for training. So again, splitting it into testing and training, and then separating the prediction value or the ground truth Y from the X's. So let's then make sure that we have the right thing. So it should be 8. This is the number of items in the training set. So next part, we will build a model. So let's see how that happens in a little bit more detail. So again, if you look back at the network diagram we made, there is going to be an input, which is our input layer, which has 8 parameters per data point, right? So, and we'll name that the input layer. And we are going to add 2 more layers, and these are going to be dense layers. So dense layer is essentially the fully connected network, which means every node in the input layer is connected to the first dense layer, and then in the next dense layer, everything else is connected to everything else as well. So we have 32 and 32, so there are 2 layers there, and input is again 8 elements in the input layer. And then finally, we'll collapse it all again to a final dense layer, which is going to have only 1 node. So that is your output. So you take 8 as input, add 32 as the first dense layer, another 32 as the second dense layer, and the 1 node as output layer finally. So that's how you build your network. And what we can do is we can now start compiling this model. So when you compile the model, you're basically getting it ready for training. And then for training, you would need some kind of an optimizer to do your gradient descent. And the gradient descent operation can use different kinds of optimizer. And the one we are using here is RMS prop. There are other kinds which we will go over later in the class. And then the second part is we have to figure out what kind of loss function are we going to use. And there are many kinds of loss functions. And this particular example, we are going to use the mean square error that we had for regression last time, which is what the loss function would be. And in addition to that, we can have another set of metrics that we can measure while we are training. And in this case, we are measuring something called mean average error, which is similar to the mean square error, except you don't have square. It's just a mean average error. So this is how you set up for compilation. And there is something called a learning rate, which is when you do the back propagation. Remember how we adjust the weights slightly after every pass, and how much you want to change those weights after every iteration. That is the learning rate. So we can keep the learning rate small for when it goes smooth and nicely. We can make it large if you want to take very large steps, but then that causes jumping around of weights too much. So there we're going to use 0.001 and see how it works out. So all these factors you can experiment with and change, and that's somewhat of an art form of how to take your particular model and adjust all these factors, which loss functions to use, which learning rate to use, how many layers you want in between. So the only thing that is fixed in this case is the input layer, because that's how our data is, and the output layer, because we are predicting one value, that is the home price. But rest of it we can experiment with and see what works, what doesn't work, and keep adjusting them. So let's execute this cell, and this will print out a summary of the model. And there you have the summary. So this is, again, trying to describe what we just did. So we have an input layer, and a dense layer, second dense layer, and the output dense layer. So number of parameters here is the number of nodes in each of those layers. And how we arrive at that is essentially you have 8 input nodes connected to 32 input nodes in the first dense layer. And this extra 32 is something called the bias nodes. And these are essentially, you can think of them as the y-intercept in the regression. So if you execute this cell, that's 288, and that should match up with the number of parameters in this particular layer. And the second layer would have, again, 32 inputs going into the 32 nodes, and then plus the 32 bias layers. So that should add up to 11056, which is right here. And the last layer should just have the bias nodes plus the one output node that we have, that is 33. So all this should match up. So these are the number of parameters we are dealing with here. So as you can see, even for a very modest 8 input nodes and 2 simple dense layers with the 32 nodes each, the number of parameters is huge for this network. So you can imagine for larger input, when they talk about GPT-3 trained with a billion parameters, this will be so huge that we won't be able to fit it all in memory. And that's when you start needing GPUs and other distributed mechanisms for taking your data and feeding it into the things. So for now, we will work with this smaller subset. Even though it sounds fairly large, we should be able to handle that interactively here. So let's take a break, because I covered a lot of material. So if you have any questions or doubts or any explanations that you need, let me know, and we can talk to it. I'll take a sip of water, and I'll wait for your questions. So the question from Maria about the bias parameters. So the bias parameter is when you do the calculations, you need one of the nodes to operate on the constants, and that's exactly what a bias node is. So think of it like a homogeneous coordinate in a 3D transformation. And that equates to one bias node per node that you have in any of the layers. And again, it basically helps to add a constant in your equation. So somebody has a question about how to load an image in Colab. You just want to load a graphical image. You can use the web address for that image. And then I think it's more of a procedural question that I'll probably leave it to figure out through the SVs or other people. So in some models, the final layer is using a function sigmoid. Why are we not using any function here? So we are using sigmoid, so I'll show you where. But when setting up the model, sigmoid or rectified linear unit is a mechanism, as I said, to introduce non-linearity into your model. So we will be using that, not just in the final layer, but in every single node that we use. All right, so let's get back to the housing classification. So this is where we use, this is the activation function. Again, this is being used in every node that we have here. So we don't probably need it in the last layer. So I think that's enough of non-linearity that we have introduced in the 64 nodes that we have. So we can get by without using one. All right, so where were we? We compiled the model, we figured out the shape of it, and we kind of looked at how these numbers came about. So this is another nice API within Keras to plot your model in a nice way. So we'll show that. So this is nice graphical way of plotting the model, and you get a clear picture of how your model is constructed. And usually I use that to make sure that that my model that I wanted is the one that is being created, and it has nice information about the sizes and then what is going on in our model. So now we have the model ready. We are going to train, and training is called fitting in TensorFlow. And the way we do it is we give it the X, which is the input data for training, along with the ground truth. And there is some parameters here. So these parameters are important. And let me go over each one of them in detail so that you know what they are. So first one is called the batch size. And we have a batch size of 16. So the reason we use batch size is we have about 13,000 input data points, right? So if we have a choice, we can take each data point, pass it through the entire network, adjust the weights, do the back propagation, figure out the difference between the predicted value and the actual value, and keep doing that for each data point. So that causes a lot of computation overhead. So instead, what we do is we do this for every batch. So instead of operating the entire network on a single input at a time, we do it a batch at a time. So we only adjust the weights after each batch is done. So that by choosing some batch size, the speed of evaluation becomes faster. So that's the only reason to use batch size. And the number of epochs is how many times you run the entire data set through. So this is a number that you can use. You can increase it for running the data multiple times through the network. So this is one epoch means entire data set goes through the entire network in batches of 16 one time. So that's all well and good. And the next parameter is something called a validation split. So in practice, when you are training, you will train and look at your results. And if they don't match your expectation, or if you need to adjust anything, so as I said earlier, you could adjust the batch size, you could adjust the number of epochs, and you could adjust things that were there earlier. You can change the loss function, you can change the number of nodes in your network, you can add a layer, remove a layer. So there are many things that you can play with. First time when you train your network, it's not going to give you the right answer most likely. So you'll have to adjust these things. So you don't want to test with the testing data when you are training. You want to have another set called the validation set, which is what you're going to test with when you are training. So once you're satisfied with your training and you think the results are good, that's when you test with the testing set that we set aside earlier. So while you are training and you adjust the different hyperparameters, you are going to use something called a validation split. So TensorFlow Keras will automatically do that for you if you just specify what percentage you want to be for validation. So that's the parameter validation underscore split. And then we have verbose as we know what is going to go on. So again, just to recap, we are going to train given our training data and the ground truth y in batch sizes of 16 for 20 epochs, which is all the data is going to run 20 times through the network. And we'll have the automatic validation happening as we do it. So let's train it. So let's run it for shorter time so that it will finish. So here it is running. So we are running 10 epochs, and it finishes pretty quickly. And you'll see that number of epoch, out of 10, and then it will finish it up after the 10 epochs. And then 680 is the number of batches that are running. So this went by pretty quickly. Otherwise, you will see this thing progressing for each batch. And these are the values of the loss that we saw. And then we were also tracking the mean average error that is also being shown. So what you are looking for is the loss to go down in value as we are training, and which looks like it is going down. So that's a good sign, which means our network is learning. And in the limit, the loss should be close to 0 as possible. We don't want it to be 0, because that would mean that the network is kind of memorizing the data. That's not what you want. And then we also have a validation loss here, which should also be decreasing in lockstep, but sometimes it may not. So again, all these numbers are hard to look at like this. So what we want to do is plot them instead. So let's do that. We plot things using something called matplotlib, which is a third-party library that we have installed earlier, and we are going to plot this. So the way we plot it is when you ran model.fit, it stores all the details about the training process into this big object called the history. And we are going to query that history object for all these values throughout the training process, and just plot them. And I label them each, and let's see what it looks like. So as you can see, the loss is going down, and the blue one is the training data loss, and then the orange one is the validation. So both are going down, which is a good, this is what you want. So ultimately it will start going down, but it will never quite reach 0. That's exactly what you want. And then it'll start tapering off and become almost horizontal as it gets closer to 0. So this is a good training. So we can be confident that this is working well. So many times this is haphazard and this is not converging at all. So you may need to adjust some of the parameters that you have there. So if you have your learning rate to be too high, or if your model is not correct, then this graph would be a weird shape that you don't want it to be. You want the loss to be gradually decreasing over time as you train. So this is good. And this also, like most of the time that you spend training something, you would spend a lot of time looking at graphs like this and making sure that your model is performing. We have a small data set and a small network. We can train this interactively, but imagine some large network with millions of parameters where it would take days and weeks to train. So there is something called TensorBoard in TensorFlow, which we might cover in a later class, that gives you better abilities to plot and version things. So you can plot things over days and come back to them and see how they're progressing. So, but for now, for an interactive plot like this, this should be sufficient for us to track things. So this is great. So the model is converging, and we can now actually evaluate it. So this one way to evaluate is just call the evaluate. It will give you the loss function final result. And although this is not extremely helpful, it just gives you some number that you can see, like what the final number you ended up with. But what you really want is to see a gradual decrease of the loss. So now we are ready. So we're ready to predict from our testing data set. So we're happy with our network. So maybe we were not happy. So you don't want to test yet if you're not happy with your model. So you want to go and adjust it so that we can test on the validation data instead of the final data. So let's try adjusting some things. So let's see if we increase the epochs to 20. Let me run it for a little bit more time, see if the loss goes down farther. So imagine the loss had stopped at 0.167. Let's train it now for 20. So which means the data is going to run through 20 times through the network. So let's see, it's converging, loss is decreasing. All right, so it looks like it's kind of stabilized around this time and it's not decreasing anymore, and that's fine. We could see now what the plot looks like. And the plot for the training loss is still nice and smooth. The validation loss is jumping around, and that's still kind of, if you look at it this from a little bit of a bird's eye view farther away, you can still see that the pattern is still like the loss is decreasing. So that's still good. And we ended up with, instead of a loss of 164, we ended up with 139, which is pretty good. So let's, now we say we're happy with the network. Let's predict from the data that it has never seen. And the way you do it is you call this predict function with your test data set, and it will put the results back, the prediction results back in this variable. So again, all these methods operate on the large array of the X test, so you don't have to run it in a for loop. It is a vectorized matrix operation, and it happens pretty fast. So under the hood in TensorFlow, all these matrix operations on the tensors are happening, and they happen pretty quickly. So it's a C++ implementation under the hood that is providing you with a Python API to interact with. So you don't have to write a loop for testing each data point. This is going to test the entire array of 3,400 points and give you 3,400 results. So there it is. It's done. The prediction should be fast for most machine learning models, because all it is doing is evaluating using the weights that it had accumulated through training. It is just going to do multiplication of different weights and values at each of those nodes and add them up. And because we are approximating a linear function or mix of linear functions, the prediction should be very, very fast. So again, we should have results in this p-test variable of all the 3,400 test data points. So let's take a look at what we came up with. So because we also have the ground truth for this test, we can compare how far off the predicted value is from the ground truth. So the way we can plot this is values versus predictions. And if you run this, there you have. So ideally, and this should be a fully diagonal line, and all the points should fall on that. And it is pretty close. And I drew a diagonal line just for comparison, because the prediction value should exactly match the true values in an ideal case. And as you can see, they are fairly close to the prediction values. So they will never match fully, because that's not what we want in the first place. And secondly, because we are trying to minimize the error, it will get minimized but never be equal to 0. So for new values, we are getting fairly good predictions. There are some outliers on the right side that you can see, and maybe the data was wrong, or maybe something else is going on there. But for majority of the cases, imagine these are 3,400 points, and they're mostly along the diagonal. So it is a pretty good prediction. And so that's one way to look at your prediction, to see how good they are. And you want them to fall along the diagonal like this. but you also want them to be normally distributed, by which I mean you want most of them to fall along the diagonal and only a few of them to be outside the range in both positive and negative directions. So you want it to be evenly distributed about the diagonal. And one way to look at this is by plotting the difference between the predicted value, which is this is how you do that. This is the ground truth, and this is the predicted value, and that is the error, which is the difference between the two. And then plot a histogram. So histogram with 25 bins, and let's see how that looks like. The histogram should look like a normal distribution, which it does. So as you can see, most of the error is 0 for almost 900 of the input points. The error is 0, which means they are exactly on the diagonal. For some of them, there is some error on the positive side, some error on the negative side, and so on. So these are the extreme outliers. There are a few of them, very small numbers on both sides. And this is not a perfect bell curve, but it is close enough that we can say that our prediction is very good and we can trust it for most of the new values that come in for prediction. So let's take another pause. So this is how you do regression. Again, you can change any of these input parameters and try them out for different things. You can add a different, when we built our model up here, we can add just another layer. I think that's as easy as just copying this line and pasting it. And we can call it this one, 3. So and you can see just through one line of code, we have added just another 32 nodes in the middle, and number of parameters has exploded. That's okay. And we can look at our plotted model. There is the extra layer. And now we can train it. So now you'll see that the training is a little bit slower, but still pretty good. And you can see the loss will start decreasing, which means the model is still okay. And at some point, you can't just keep adding more nodes. And I think what would happen is, because there'll be so many nodes, that the network will kind of start memorizing the data. And you, again, it's an art form and as balancing act to figure out what is the right number of nodes for a network, and how to optimize for that. Because the more you add, more computation it takes, and then there's a more risk of overtraining. And it's still working. I think it's pretty good, but not as good as before. So maybe you need to train for longer. So you can get into this phase where you are constantly trying out different things, trying to get your loss to as small as possible by varying these different parameters. So ultimately, you'll get to a nice state where you can. So this still looks pretty good. It's training pretty well. And so not much has changed. So one other thing we can try is make the learning rate even smaller. So which means it will adjust the weights ever so slightly. Let's not change the things. So it's still going pretty good. So you can play with the batch sizes and other things as well. So again, I'll take another pause. We have about 5-6 minutes remaining. And have any questions? So this is a multi-step process that I want you to kind of understand, and this is what we will be doing. Regardless of the kind of problem we are solving, you would be doing these steps. So it makes sense to kind of understand these because there may be different kinds of data, different kinds of models, but ultimately what you will do is these list of 7 steps for any kind of problem that you solve. So first you try to understand what you're trying to predict, collect the data that you need for it, prepare it, clean it up, do some analysis, visualize it, maybe remove duplicate data, do whatever you need to do, and do the normalization of the data if you want to process your features and prepare them. Then you build your model and train it and evaluate the quality of the model. What we did by adjusting different things, you can get your training loss to be as low as possible. And then finally, when you're happy with it, you can start doing predictions. So this doesn't change. So this is the heart of how you solve different problems using the machine learning method. So we did all of that for the housing project, and then we'll cover some of these things in how we looked at the data and processed the features. We did the normalization, keep 20% for testing, separate features from the labels, and built this network. So now this should seem very familiar to you because we went through the process of creating this and compiled the model. And then we trained it. The first part I have in yellow there, and this you can predict the model even before training, and that will give you random answers because initially the weights are initialized to be random, but it will at least give you an idea of the sizes of the inputs and the outputs, so you can test your model without having to train first, because training can sometimes take a while, but you can still test your model to make sure that the sizes and the dimensions and the values are okay. And then finally, we did the prediction. All it took was 1 line, and then we plotted them. It all worked out fine. So as a homework, what I would like you to do is try to improve on these results, and then you can tune the hyperparameters. The hyperparameters is a general term we use for anything that we can change during the training process to improve your model and improve your learning. So you can try different learning rates, try different optimizers. There's another one called Adam that you can try. Different loss functions make network deeper, more layers. So you can try all of these things. Let's go back to see if we have any questions. So some of the factors that go into deciding how many layers to use will depend on the amount of data that you have and the number of parameters that you have in your data set. So for the housing, we had 8 input parameters. We had about 17,000 data points. So if you have fewer data points, you want to use a smaller network. The more, the bigger the network is, the larger the number of nodes, more likely that you will overtrain, and each node will then somehow figure out what the actual data is and memorize it, and will just spit it out back as a, so you'll have perfect training, but the predictive results of that kind of network are going to be low. So again, it's an art form. You can try different things, but the larger your data set, larger the number of parameters, the bigger or denser network you can use. So the validation line is going to be a little jaggy, because what happens is the validation set is chosen from the training set. So parts of it, the network has kind of seen before, and it kind of knows about it a little bit. So it is okay for it to be jaggy as long as it's trending downwards. And to get better results or better, so that it's not as jaggy, it's not doing that much variation. Again, to have it's an interplay between the density of the network and your data size as well, because some of the validation data may be outliers, like we had. So there's always going to be some issues with your data, that the parts that you're keeping aside, they're not as accurate. So it's okay for it to jump around, because it's a very small subset of your data. So and that is also like similar to the prediction that you're getting. All your answers are not going to be 100% accurate. All this is an estimate. So machine learning will always be an estimate of your answer. It's never going to be exact. So that jumping around is okay. But if you look at the scale of the y-axis, that jump is not huge. It's actually pretty small. Okay, one more question. Right. If you retrain without redefining the model, will the training start with the previous weights? So that's a good question. For our setup in Colab and TensorFlow like this, yes. So because it will retain everything when you execute the script, because we have them as snippets, not as one big program, it will re-execute it from the place where it was before. So if you don't redefine the model, don't change the parameters, then it will take off from where it left before. So it's a good way to kind of pause your training and then come back and do it again and do it again. So this, like if you have small amount of resources, that's a good technique to kind of, because sometimes accidentally you'll change something, and if you're writing a big program yourself, you accidentally change one variable and then starts the whole process all over again. So this is a good idea to keep retraining without having to recompile or redo your model. All right, so let's stop here. So we didn't get to the flower classification today. We'll do it in the next class, and we'll cover classification, and that will push us into understanding more about distributions, and we will converge on the definition of how linear regression least square is very similar to the minimum likelihood. So this would be an interesting lecture next time. So again, thank you for being with me today and talking to Bindu. Again, we'll take her advice on, like, most of this data is going to be easy to use, and because it's prepared and cleaned out already. And we will deal with some real life data also in one of the future classes. All right, thank you again, and I will see you next time.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.